X gon' give it to you. Fuck, wait for you to get it on your own. X gon' deliver to you. Knock, knock, open.
What's up, nerds? Welcome back to Tea Time with your favorite software engineer. If you guys are new to the channel, check me out, subscribe. I post LeetCode videos a few times a week. I'm trying to grow this channel to 10 subscribers a day, so help me out with that. I also started a Slack channel. It's got over 1,000 members already. I post LeetCode problems for us to discuss and solve every day. So the invite link for is in the description below. So today I actually got requested to do this problem. I'm going to go over sum of nodes with even valued grandparent. So given a binary tree, return the sum of value of nodes with even valued grandparent. So a grandparent is a node, is the parent of a parent. So the grandparent of 2, 7, 1, and 3 is 6. The grandparent of 9, 1, 4, and 5, or 9, 1, and 4 is 7. 5 is 8. 6 doesn't have a grandparent. 7 and 8 don't have a grandparent. So we just want to return the sum of nodes that have an even valued grandparent. So we would return 18. Because 6 is even, so we would add 2, 7, 1, 3 to get 13. 8 is also even, so we would add 5 to 13. We would get 18. We just want to return that. So let's go to the whiteboard. The way I thought about how to do this is I just typical DFS function. So we're going to go down the left side and along the way check to see if they have a grandparent, if the grandparent's value is even, and then we're going to go recurse back up and go down the right side and so on. I've done so many recursive problems, it just comes naturally. So let's go over this. We're obviously just going to want to have a sum first, initialize it to 0, and then we're going to want to check if first we're going to want to see if there's a grandparent. So if grandparent does not equal null and, sorry, that's my and, grandparent val mod 2 equals 0, then we're going to add it to sum. And then here's where the Dfs Recursion comes into play. So let's check. Now let's check to see if that node, the root, if root.left does not equal null, if it has a child on the left side, then let's call the Dfs function. So Dfs, then we're going to, so the Dfs function is going to look like root parent grandparent. So this is in these recursive functions, in these recursive calls, we're going to be changing root and parent and grandparent. We're going to be updating them. Whoops. So then we're going to, damn it. We're going to pass in root.left as root, root as parent, and parent as grandparent. So it's getting updated. And then we're just going to do this same function. I'm not going to write it out again with root.right. So let's go ahead and code that. So we're going to want to have a sum int sum equals 0, and our base case is just we're going to want to see if root is null, then it's empty, so let's just return 0. It's an empty tree, and let's call our function. So let's pass in root, and in this case it's going to be the parent. Since we're at the root, move my iPad. Right here, so let's pass null. It doesn't have a parent, it doesn't have a grandparent, so it's both going to be null, and then we just want to return sum. So now let's write our Dfs function. So it's going to be void. We're not returning anything, we're just calling it. So Dfs tree node root, tree node parent, and tree node grandparent. Okay. And not going to zoom in more. Okay, so we didn't pass in sum. We can't put it in this function because we can't initialize it. It's a recursive function and get reset every time. So let's create it as a global variable. I'm going to erase this line. And so the first thing we want to do is if root equals null, we passed in this is in the case where if it calls a child that's empty or null, we would just return the function. We don't need to do anything. And then let's check if the grandparent's value is, we're going to do this if statement. If it has a grandparent, if grandparent does not equal null and the value is even, so we use the modulus symbol. Sum plus equals root.val. Okay, and now we just want to do these two if statements. We have one for left and one for right. So if root.left it's not equal null, we just want to, this is just saving us time. We want to make sure that we don't want to call a recursive function to a null child, basically, because there's no child there, so we don't need to do anything. So this is just, this if statement is just saving us a little time. We could just do like dfs root.left and root.right, but they both work. This is just a little more efficient. So let's do dfs root.left. So this is where the root becomes the parent and the parent becomes the grandparent. And let's copy this. And the same thing for right. So let's just change left to right. And that should be it. Let's run it. And grandparent modulus 2. If grandparent does not equal null and grandparent. So I'm doing something wrong here. If grandparent does not equal null. Oh, grandparent.val. That's why. There we go. And submit it. Sweet, 98 and 83, so it's really efficient. So the runtime for this is just O(n). We're going through every node. We have to check every node's grandparent. And same for the space complexity. Our recursive stack could be at worst O(n) if the tree is all the way to the all one-sided, either left or right. It's going to have every single node in that recursive stack. So it could be O(n) in the worst case. So let's just go over the recursive stack. Basically, it's going to start here. It doesn't have a grandparent, so it's not going to execute this. It's just going to call dfs root.left. It's going to go to 7. 7 doesn't have a grandparent, so it's going to call root.left again. Well, 2 does have an even grandparent, so it's going to add it to sum. So we add 2 to the sum. And then it's going to call, well, 2 has a left child, so it's going to call this. Go down here. This does not have an even grandparent, so it's not going to add it to sum. It doesn't have any children, so it kicks back out to 2. 2 doesn't have a right child. We're right here right now, so it's going to kick back out to 7. 7 does have a right child, a 7 right here, so we're going to call this function. And then, so we went to the left side, we're going to the left. So this one does not have an even grandparent. 7 is not even. So it doesn't have any more children. So it's going to kick back out. 7 is going to call the right child. And this doesn't have an even parent either. It doesn't have any children. So it's going to kick back out all the way up to here. And then we're going to go to the right, left, kick back out, right, right. And it's going to add as we go. It'll add 1 and 3 and 5. So that's all there is to this problem. If you guys learned something, this video helped you, make sure you smash that like button, and I will see you in the next video. Thanks for watching.